There's one more day of workshop, is it? Tomorrow's the last day, or?
Yeah. Tomorrow is the last. Okay, so I'll start. So good afternoon, everyone. On behalf of ISA Bangalore students, I welcome everyone to the Limits Mathematics Online Camp. So today we have Professor Yogeshwaran. He is a professor at ISA Bangalore, and to a few words about him is he did his PhD from University Pere at Maiduguri, followed by a postdoc at Technion, Israel. And 2017, he was awarded the Young Scientist Award by the International Science Academy. And his research interests lie in probability theory, and to be specific, in stochastic geometry, random labs. And with great honor, I welcome Professor Yogeshwaran to deliver this talk.
Okay, thanks a lot, Sanchayan, for the kind introduction, and thanks to the students for organizing this for quite a few years now, I think, and also for inviting me. It looks a very impressive list of speakers, and with great enthusiasm they are having this. Hopefully there will be more such events, and maybe in future they will even have some offline events at some point. So I'll be speaking about something that in the last few years has caught my interest, and of course at the end I will talk about a more elaborate history. One quick thing is that I'm writing on my iPad and screen mirroring due to a reason I cannot see the chat or even if who's there and so on. So in case there are issues or you're unable to see or something is not clear, and also any mathematical questions, please feel free to interrupt. It's not necessary I cover everything I have, but it's more important that there are as many discussions as possible. Okay. So the thing I decided to speak about today is so it's about optimal matching of random points, random samples. And a good reference for this is there is a monograph or a Springer book called Mathematics Going Forward, which has a collection of survey articles by experts in various subjects, out of which one of them is by Michel Ledoux, who's contributed a lot to this topic and who's written an excellent survey on this question. Okay, so I will say what I'll do roughly. I said there will be, I indicated in my abstract two questions, one an integral or a analytical question, and a second a combinatorial. I'll outline the framework for the first question, do some simple computations, what we can do, and then say how it leads naturally to the second question, and again some simple computations in the second question, and then indicate what is known, some background history. And since it's for undergrad students or students, there'll be a lot of exercises along the way that hopefully should be doable by many of you, and hopefully you can try during the talk if you get bored, or after the talk as well. Okay, so this is the brief outline. So let's start with the basic. Okay, so here is on numerical integration. Okay, so we have a function, let's say from 0, 1 to r, which is continuous. Okay, and it's a continuous function, so I trust all of you know this. And then I will set, for ease, I will just write integral f to mean integral f of x dx. Okay, so it's a continuous function on a compact interval, So the values are bounded and it's integrable in whichever sense you are comfortable. Let's say in the sense of a Riemann integral, you can do it. Integral is some real number. And also because of what I said, I'll define f infinity is supremum, x belongs to I. I'll let I be the unit interval and mod f of x. Okay, and this is finite. So where I is the unit interval. Okay, so I assume all of you have seen this in analysis. Okay, your basic analysis. And this is what we have. And of course, a basic fact is from all this, you can definitely check. This is integral 0 to 1 is the integral is bounded by the maximum because I've just taken it over the unit interval. So you can always say this. So if there is any issue or if you feel something is incorrect, please feel free to indicate. So this is one ingredient. And let's say I want to compute this integral, that someone wants you to compute the integral. Of course, if they give you the full function, this is very easy. But if you are given the function only value at only some points, then it's a bit more harder. And this is what we want to address. Okay, so the next ingredient is I'm given x1 to xn. I'll say these are IID uniform random points in 0, 1. Okay, let's parse the statement. Okay, I assume by going by syllabus, some of you would know what's a uniform random variable. So what does it mean is that the probability xi, that is, I pick a point randomly in the unit interval. So the probability, it belongs to some interval AB, is b minus a, where you have 0 less than a less than b less than b. Okay. So with the probability, a point lies in an interval, the random point lies in some interval, is equal to the length of the interval. Now, this is what I say uniform random point. What does it mean to say it is IID or independent and identically distributed? So I want to say what is the probability xi belongs to ai comma bi for all I. This, they're all independent, meaning that the probability each xi lies in some interval ai to bi is the product of the probabilities. Okay. So this is what we mean by saying that xi's are independent, that it is a product, and each of them is uniform random. Okay. So the next bit is they're all identically distributed and as uniform random points. So this is and again for convenience, I will assume that the intervals, all the intervals are within 0 to 1. Okay. So is this clear? As I hope everybody has seen this in some form. So you should have definitely, I assume, seen what's a uniform random variable, that its probability is proportionate to the length of the interval. Now, if I ask you n many of them, each of them has to be true, and the probability that all of them lie in some interval is product of the probabilities. Okay. Okay. So now let me go to the next slight generalization of this fact. Is I've told you there is a function f. Okay. And then expectation function f of xi. What is xi is a uniform random variable. F of xi, this is some, I don't know what, but this is some random variable. It's a random number, right? So it is a random number in the real line. Xi is a random number in 0 to 1. F of xi is a random number in the real line. I can ask its average or expectation. So E stands for expectation. Average or mean, whatever is what you're comfortable with. But simply in this case, if you have not seen it, I'm defining it for you as expectation f of xi is 0 to 1 integral f of x dx. Okay, this is simply the integral. So expectation f of xi is nothing but the integral. Okay, for example, if I take f to be indicator a comma b. Okay, so this is an indicator function, which means that f of x is 1 if x lies in this interval, otherwise it is 0. In this case, what is expectation f of xi is nothing but b minus a. Okay, which is also by definition, it's true, this is same as a2. Okay, so this is nothing but a revision of a very basic probability facts. Okay, this is simply I'm repeating or recalling, making you comfortable with what you have seen and just setting up notation, because I trust these are undergrad students from various parts of the country, and the notations, as we know, these keeps changing depending on where you have studied. This is the first fact. Now let me take functions fi and continuous. I will always assume continuous for convenience. Okay. Then the next thing I'm going to say is, what is the probability I equal 1 to n fi of xi? Okay. And this is nothing but probability I equal 1 to n, because they are independent, xi's are independent. This is a product of expectations because they are all independent. And now, furthermore, this is I equal 1 to n. Now let me use my abbreviation. You see, I introduced the abbreviation because at some point in screens and board, you are going to write at the corner and it is convenient to have the abbreviation. Then I don't need to go to the next line. So this is integral f by, sorry, it is integral fi. Okay, this is integral fi. So which is to say it is integral of fi of x dx from 0 to 1. And this is because xi's are uniform. Okay. This is the formula we used in the no. Okay. Switch back to this. Okay. Oh, there's a way I could circle or stuff, but I didn't figure this out. Okay. Okay. So this is this last bit. This is exactly this formula I'm pulling from the top. Okay. So this last time, I've just for each expectation fi of xi, each of them is an integral. That's exactly what we are given. Maybe at the top, I'll just recollect this is same as integral f for me by definition. Okay. I hope this is clear for everyone, but let me end with one maybe exercise, which is quite useful, right? So I'll give a exercises. What will be the exercises? They're going to be one or two extra, one more later. So y is a random variable. Y is a random variable. Okay, it's an abbreviation. Maybe I should write the full form. With R values, real line, right? We all know what is expectation, and we all know that variance of y, you have multiple formulas. I'll use say you can use, you may have seen one or two of these formulas. And now what I'm going to ask is the following. What I'll ask you to prove, you can prove from whatever we have seen so far. Yes, this variance is integral f square minus integral of f whole square. Okay. And by definition, you see variance is always non-negative. And I will at least put a very simple claim here to remember this mod f infinity is the supremum. What we have defined before, f infinity is the supremum of f. Okay. And then I'm asking you to check this. Okay. So this is the second thing is the exercise. What I have underlined to show the equality and the upper bound. Okay. I will use this exercise even if you cannot do now. Please note it down and you can try it later. This is something I will use later. That variance of f of x is less than 2 times. And this is clearly, by my assumption, this is finite. And this is some finite number. I don't care, but some finite number. Is it good so far? I hope I'm still audible. I'm still.
Yes, you are audible.
Yeah. I've completed 3 pages just so that it's clear that we are right.
Yeah, yeah.
Okay. Okay. So this is the first set of exercises and first basic fact, just recapping what's expectation, what's integral. Okay. And if those of you who are not comfortable with expectations or who have not seen this, you can always take the integral definition wherever it is given. Okay. And we can work with that. Okay. Now, what is the question we are asking? Let me make the question clearer. Okay, given f of x1 to f of xn, how do we compute integral f? Okay, so this is the question I posed, that you have a function. I'm not telling you the function, I'm telling you it is continuous. I'm telling you it is remember on the, its domain is the unit interval. I'm telling you the value of function at some random points. Okay, and now I want to know the value of the integral. This is very common in various situations, that you are given some random values of some object of some function, and you are asked to guess something about the function, in this case, integral of the function. Okay. So what is a reasonable guess? Well, what is reasonable? Many people who have seen probability would know, but even if you have not seen probability, if you have just done basic integration or this, what do? You will just take the average of these values. Okay, you take the average of these values and you think this should be the function. Okay, this should be close to the integral. Okay, what is the average? Let me define. I'll call this the empirical average, empirical mean. This, we define it to be Sn, is defined as 1 over n summation I equal 1 to n f of x. Okay, I'm given observations of the function at n random points. I want to know the integral. So the easiest thing and to say is that take the average of the function at these n random points. And what is the guess? For large n, okay, for large n, Sn is very close to integral f. This symbol means approximate in whatever sense, okay? That is, Sn is very close. This means approximately. The precise meaning is irrelevant at this stage, but in some sense. These are two real numbers. One is a random number, one is a deterministic number. Sn is a random variable, okay? It's a sum of, as we said, xi's are random variables, f of xi's are random variable. The sum is a random variable, then 1 over n is another random variable. Okay? So Sn is some random variable, and we are thinking it's close to the integral f. Why is this true? Why do we believe this? And is there some justification behind this? We will see one of the most basic, what are called the basic method in probability. Okay, it's called often the first moment and second moment method. It is to compute the first moment, the mean, and then the variance. Okay, which is why I introduced the variance and the mean. Okay, if you compute the mean and variance, you can get a lot of information. You will see why. Okay, so first let's some simple computations. What I said. So this is the question. Any clarifications also? This is my first question, phrased very precisely. I want to know, is Sn very close to S? Sn very close to integral f? Does it converge or not? Okay. As n goes to infinity, I want to know if Sn converges to integral f and in what sense. Okay, some of the organizers are, I guess, students who have done courses with me and others, and many of them would have seen it, and possibly many of you would have seen this type of question in various places. But let's go through it for benefit. If you haven't seen it, it's a very good thing to see. Okay. Now, mean and variance. Mean and variance of Sn. Okay, what do we do? Mean of Sn. It's expectation of Sn. It's expectation 1 over n summation I equal 1 to n f of xi. Okay. So no matter what you have done, discrete or continuous random variable, one of the most basic facts you would have seen is what is called linearity of expectations. So let me write it. Linearity of expectation. What does it mean? I can take a constant outside the expectation, first thing. I can take the constant. I can use the same fact again to say that expectation of sum is sum of expectations. Okay? Expectation of sum is sum of expectations. Again, many of you would have seen it in various contexts, but it's simplest to think of integral. For those who have not seen it with expectation, see, you would have seen it with integral. Okay, instead of expectation, if I wrote integral, all of this is true. Okay, integral of the sum is sum of integral, and all this will be true. And so you can, I can write this. Okay. And now, by definition, what is expectation of integral? You know, we have defined expectation f of xi. That is, by xi's are uniform. So this is 1 over n summation I equal 1 to n integral f. No matter what I, all the expectations are equal and all of them are equal to integral f. And now this is simply integral f. Okay. So the important thing from this step, even if you have not fully understood the question, is to remember the definition of Sn. Okay. So I'll again recall, I'll again highlight it. Sn, xi's are uniform. So far, everything I've done has only led to this, that I have defined, if you have seen already uniform random variables and basic probability, all I've said is take n independent uniform random variables, x1 to xn, f is a continuous function, and then I'm taking sum I equal 1 to n f of xi, 1 over n sn. Okay, and then I've computed the expectation. So we have our first fact, expectation Sn is integral f. Okay, I'll call it 1. Now let's do the next thing. So illustrative thing, someone gives you a random variable. First thing you try to see, okay, try to understand its expectation. Once you have understood expectation, try to understand the variance. Okay. Okay, let's try to understand the variance. And now I will use the how do I understand the variance? I have to understand square variance of Sn okay. So this is what it will be. Then here is this is one way to do it. Okay, I will ask you to, you can also do a checking and so on and see if what everything is I'm saying is true. Here is a second exercise I'm giving you. Exercise 2, variance of Sn, which is variance of 1 over n summation I equal 1 to n f of x. This is just the definition. But here are facts. Expectation, when you pull out a constant comes out. In variance, it becomes a square. Okay, you can check. This is trivially from the definition. Okay, so this is 1 over n square variance of summation I equal 1 to n f of xi. Okay, and this is what you will get. And then variance of sum of independent random variables. So f of xi I equal 1 to n are independent random variables Okay. So these are independent random variables. Variance of the sum, you can check, becomes, this is the main check. Either you have seen it, in which case you can try to reprove. If you have not seen it, try to prove it. So this is an important thing. Okay. This is summation I equal 1 to n variance of f of xi. Okay. So this is an important fact. The next fact, like with expectation f of xi is same for all I. Xi's are all uniform. So what does it mean? All the variances are equal. So you will get summation I equal 1 to n variance of, let's say, f of x1. And this becomes easily, okay. The main thing in this entire thing exercise is the middle equality. That variance of sum of independent random variables is sum of variances. For expectation, it's just linearity. We don't use independence at all. But in variance, the independence is very much needed. Okay? Okay. And then what is the conclusion from here? I will point out one thing, one fact we are going to note for future. So variance of Sn is variance of f of x1 by n. Okay, so we have this piece of information. Now remember, I gave another exercise earlier. Maybe I should have marked it here. Exercise 1. Variance of f of x, or in this case, I should have put, there's a typo, x1, let's say, or xi, is less than 2 times f infinity square. Okay, variance is upper bounded by this. So what do I have? Is I have variance of Sn is less than 2 times its variance of f of x1 by n, each of which is bounded by f infinity square. Sorry, I put it, which is fine. Well, I don't care finiteness, which is my equation 2. Okay. Okay. So the big fact, if you have not completely even followed the details, expectation Sn is nothing but integral of f. Variance of Sn is at most 2 times f infinity square by n, which is some finite. The numerator is finite, the numerator does not change with n, denominator goes to 0. Important to infinity, variance Sn goes to 0. Okay. This is what we have. Here is my next exercise. One of the last ones, you can say. After this, there will be some things I'll claim, but I won't expect you to prove it. This is exercise 3. Y greater than or equal to 0 is a random variable. Okay. Probability y greater than, that is, y is a non-negative random variable. Y is non-negative, and then there's a famous inequality called Markov's inequality. Okay, many of you would have seen it, but if not, you can prove it. Probability of y being larger than epsilon is less than expectation y by epsilon. Okay. So probability y is larger than epsilon is bounded above by expectation y by epsilon for all epsilon strictly positive. A consequence of this is the following. If you ask me what is the probability y minus expectation y is greater than epsilon, this is less than, trivially, square everything. If y minus expectation y is greater than epsilon, modulus squaring the inequality is still true. And then take Markov's inequality. I'm applying Markov's inequality here. And this will give you and this, for often convenience, we'll call it Chebyshev's inequality. This is known as Chebyshev's inequality. Okay, so many of you may have seen already both of this. Okay, so this is a recap. If not, it's a good exercise. If you haven't seen it, it's a good thing to prove this. Okay, and important here, I will say, in this case, y is any random variable. I don't need non-negative anymore. So take any random variable, this is true. The second part is true for any random variable. Okay, I don't need non-negative at all. Okay. Now let's conclude, put everything we have had together, even if you have not followed fully. One part you can see, I have an estimate on expectation is Sn is integral f. So let's recollect, put everything together. I have Sn, which is 1 over n summation I equal 1 to n f of xi. Okay, I know its expectation is integral f. And now what do we have? Probability Sn minus integral f greater than or equal to epsilon is probability Sn minus expectation Sn greater than equal to epsilon, because expectation of Sn is the integral, and by Chebyshev this is less than variance of Sn by epsilon square, which we have already upper bounded by f. I have an upper bound, I call it norm f infinity, mod f infinity. I have a strange notation for the supremum. Okay, this is what we call the supremum. Okay, so I've controlled it by something. Important to remember, the numerator is a constant independent of n. The numerator is independent of n. And the denominator is n times epsilon square. Epsilon is fixed. So the big corollary of everything so far is that this probability of mod Sn minus integral f greater than epsilon, okay, is less than equal to 2 times. That is the probability Sn and the integral differ by epsilon. Epsilon is my error. Okay, I give you a small value epsilon. I'm asking you what is the probability that based on this random data, I'm trying to estimate the integral. What is the probability my error is at least epsilon? It turns out this is less than this much. So you have a control on the error. What is more important going ahead, which is very crucial, I'll note down, is probability of this Sn This goes to 0 as n goes to infinity. It's clear. I guess this is very basic analysis. Numerator is a constant, epsilon square is fixed. So for all epsilon greater than 0, limit of n goes to infinity, of course limit not converge to 0, limit is equal to 0. So what does this mean? This means with high probability, there is a loose statement, Sn is very close to integral f. This is what we said earlier. Okay, Sn being close to integral f, I want to know how to estimate it. We are saying this is the procedure to estimate. A very simple kind of question. Okay. Now the next question, very natural in such error questions, is that I'm telling you the error becomes very, very small. As n goes to infinity, there is an error between Sn minus integral f. This is the error. I'm saying this error becomes 0. But in many, many useful questions, I want to know the rate of error. Sorry?
So the limit
Was there a question?
tending to infinity, right?
Oh, yes. Thank you. Of course. So stupid. Thank you. Yes. Thanks. Okay. I'm glad someone noticed it. That was not on purpose. Often, as I tell my students, some errors maybe I try on purpose, but not this. With high probability, Sn is integral f. Rate of error, I want to know what is the rate of error. So what do we do? Here is the following thing. You take some class of functions, f. And then we ask, take over all possible functions and ask the following question. How that among all possible functions, I want to know when is the error very small on an average. So what I have said before, we have concluded before, is that for every f, the error has to go to 0. Give me a function. Okay. What we can say from what have we done before? Before Sn minus integral f is a very famous inequality called the Cauchy-Schwarz inequality. You would have seen it, many of you, which tells you expectation of mod Sn minus integral f is less than square root of its expectation squared. Okay, and what we have shown, if you see, and this is what, this is square root of variance of Sn. We know this goes to 0 as n goes to infinity. For all f, we know this, continuous. For all f continuous, I know this expectation goes to 0, but I want some uniform control, because that is, I'm not telling you whether my function is, I've given you a function, you get some error, I know error vanishes, I want to know how fast the error is vanishing in a uniform sense. Okay, this is very important in very applications, because I a priori don't know anything about the function. If you tell me the error rate currently depends on the supremum of the function. And question is, can I somehow tell you something more universal? Okay. So here is something we will do, is now onwards, I'll fix my f to be f0 to 1 to r, f Lipschitz function. What does it mean to say Lipschitz function? F of x minus f of y is less than equal to x minus 1 for all xy in 0, 1. So any such function you can easily prove is continuous. Okay, you can check it. You should have seen it already. Maybe many of you have seen it. If not, you can take it as a exercise. Okay, that functions are all Lipschitz. Okay. And now my error En, let me define. Let me put question. This is my precise question 1. Officially, previously we did discuss. Those are leading to this, but this is the main question. It is still, there are many aspects of this question which are unknown. Oh, of course, I'm making a mistake. Okay. So I take the difference between Sn and integral f, take the expectation over all possible f. Okay. So I maybe change one notation here. I'll call this ERRN, error. Okay, and avoid confusion with expectation. Okay, this is done. Now let's slowly see or quickly see how it leads immediately to question 2. It's not hard once we have taken Lipschitz. Here is one little way to go from this analytical kind of question to more combinatorial. Let me take x1 prime to xn prime to also be IID uniform 0, 1 random variables. Okay, these are another set of independent uniform random variables independent of everything before. I gave you n, I now give you another n IID random variables. Okay, and I define Sn prime to be same as before, but now with xi primes. It is same as before, but with xi prime. Okay. Now what do you know? Expectation Sn prime is also equal to integral f. Same reasoning as before. It doesn't change. This is another set I have given, but the same random variables, same collection. You know, independent of a new collection, but with the same properties. So this also will have the same expectation. Okay. And now here is a little trick. What is the trick I'm going to do? This is Sn minus expectation Sn prime. So I have expectation Sn prime, okay, and I have taken it, I have replaced integral f by some new expectation Sn prime. Okay, I'm going to be a bit, this is a very subtle point. Some of you may not, I mean, it's not something you come across in the first kind of course in probability. But what one can do is that this can be controlled by, one can pull the second expectation outside the modulus. You can take the second expectation outside the modulus and you will get expectation mod of Sn minus Sn prime. Okay, because it's an expectation taken with respect to different random variables. Okay, so I can do this, and this is one bit. So this is a way to relate expectation Sn, the error, to Sn minus Sn prime. Now I will do another thing which is more natural. I will apply triangle inequality. Sorry, I should have started with something. I'll apply triangle inequality. I look at now expectation Sn minus Sn prime. I add and subtract mod f. I add and subtract mod f, but remember Sn and Sn prime are really the same random variables. They are both the same in distribution, have very similar properties. They are independent, but they both are same. Okay. Sn, Sn prime are IID random variables. So both of these terms, because of that, both of them are equal to error n. So this is 2 times error n. Okay, both are error n, so this is twice. So what have we proven? Important to go note forward is expectation Sn minus Sn prime is less than equal to error n. I forgot a supremum somewhere. Yes. Supremum f belongs to f 2 times error n. So error is now controlled not by difference of Sn and integral, it is by difference of Sn prime and Sn. It is controlled by expectation Sn minus Sn prime. Now, first thing I want to point out, you can forget all the earlier computations I did. Like there are many regeneration points in a lecture or in a course. I always tell students to watch out for it, and at least one can follow from that point onwards. If you didn't follow many things before, I'll quickly recap what we defined. Sn is the sum. Remember, I'll maybe even write it for convenience. Sn is same as Sn prime except with xi's. Sn is 1 over n sum of f of xi, and I'm looking at the difference between Sn and integral f modulus, taking expectation, then taking the supremum. Okay. And then what we have is the expectation of Sn minus Sn prime. I've shown you is upper and lower bounded up to some constant factor independent of n. There is a bound of only 2. It is the error. I can sandwich the difference of expectation Sn minus Sn prime between the error and twice the error. Okay. So far I didn't use Fs Lipschitz at all. Okay. Now let me do a couple of things at one go. What are the couple of things I'll do at one go? Let's do the following. So we have Sn minus Sn prime is 1 over n summation I equal 1 to n f of xi minus f of xi prime. That is every xi and xi prime I'm pairing. I'm pairing I and xi and xi prime. Okay, but you see, this is not at all necessary. What I can do is I can take a bijection pi. Pi from n to n is a bijection. It's a permutation. Bijection, permutation, whatever you call it. And now I can write this as 1 over n summation I equal 1 to n f of xi minus f of x pi of I prime. Okay. So I could have, instead of taking pi to be the identity, which I did in the first line, I'm pairing xi with xi prime. I pair xi with some other xj prime, where j is pi of I. Okay. So I can pair this in any way I like by just using it's both are the sum of two things and the differences. Now comes the nice thing. So now I want to know Sn minus Sn prime is 1 over n summation I equal 1 to n f of xi minus f of x pi I prime. Right? Remember, this is what we had in the last step. It's f of xi minus f of x pi I prime. I take the modulus, use triangle inequality, and then I get this. Now I use that f is Lipschitz. I use now that f is Lipschitz. By using f is Lipschitz, I have this property that it is mod of xi now. By just very definition of Lipschitz, this is what it is. Xi minus x pi I prime. Okay? But you remember, on this side I had a function f, and this side I have a permutation pi. There is no relation a priori. This is true for any f and any pi. So we have a very important thing. What I can do, I can take a supremum over f belonging to f, Sn minus Sn prime is less than equal to infimum over pi. I'll just abbreviate it here. Bijection 1 over n summation I equal 1 to n xi minus xi square. Okay. And thing I want to, it's beyond this lecture, it's an independent lecture someone can give, is there is something called the Kantorowicz-Rubinstein duality, which will tell you this is actually an equality. Okay? So what we have, one is a supremum, one is the infimum, but we are telling the supremum is less than the infimum, and even better, it's a very powerful concept in mathematics, occurs in various places, is that this is a duality in the sense that this is actually an equality. Okay? One can prove that this is an equality. It requires some work, but it's at the heart of a lot of results. One can see it in linear programming and so on. This is a equality. Okay, this is a very powerful result. This supremum is equal to the infimum. So this side now we have come. I've been a bit slow, but as I said, it's not so important. This side is analytical question, or if you remember, it's about the integral. This side is purely combinatorial and some geometry, because I have to match points. I have to match these 2 points. I want to find a pairing of xi and xi prime such that the total distance is minimized in the pairing. This is the cost of a bijection. For every permutation or bijection, I'm giving a cost, which is sum of the distances of the pairings, and this is what it is. Okay? So this side is the optimal matching. So this is the title now, optimal matching. This side is the integration, best integration. Okay. I think I'm close to end of my time. Can I take about a few minutes, 3-4 minutes? Is it okay?
Yeah, you can go.
Yeah, yes.
Okay. Now, so I hope the 2 questions are clear. This is my question 1 I said, and this is question 2. That is to find this infimum. And as I said, I've at least shown that finding this error supremum in question 1 is less than the infimum in question 2. That's already very nice. I get an upper bound on the error. But even better, I'm saying this is an equality. Okay? Now let me do, at least I said I won't give any more exercises, but never trust an instructor who says that. Okay, that's the next lesson. There is always one more exercise than how many ever I think. I thought I could do this, but due to lack of time, I will leave it as an exercise. How do I find this? In general, this is not very easy to find this. But let me give a trivial lower bound. I will suggest what is the lower bound. Let Ni equal to the arg min of xi prime, or let me just write it. That's better. So Ni, I'll say, is equal to xj prime if xj prime is the closest point to xi. So if Ni xj prime is the closest point to xi, okay, then I put Ni to be equal to this. Then what do you get is you will get the following. You will get that xi minus x pi I prime is always greater than summation I equal 1 to n is greater than xi minus ni for all I. Because no matter what bijection I take, the distance cannot be smaller than the distance to the closest point. Okay? And this is not in the exercise I'm giving. The exercise is the following. Is 3. Prove that xi minus ni greater than, let's say, 1 over 2n is greater than some constant, strictly positive constant, independent of n. Okay? This is greater than some strictly positive constant, independent of n. Okay, there is one constant, this is independent of n. And now this is, I should change the ink to indicate this is now a. Now this gives you indicator xi minus ni is greater than or equal to c by 2n. Okay, so from this you can prove this fact. This is an easy thing to check. If I show that some random variable has a probability of being greater than 1 over 2n by probability at least c, then the expectation is at least lower bounded by c by 2n. Now let's take expectation 1 over n, infimum over pi, summation I equal 1 to n, xi minus x I prime. Okay. Now this one, because of all this, okay, what I can do for each of this is greater than 1 over summation I equal 1 to n, expectation xi minus ni, and just by what we have argued, this will be c by 2n. Okay, so the lower bound is c by 2n. This is the trivial lower bound. Okay, this is the trivial lower bound, it's c by 2n. Okay, this is the trivial lower bound you can get. So suppose I call this question as opt n, optimal matching. What have we shown is expectation opt n is greater than c by 2n. Okay. Now let me say exactly. I will now stop any more further computations. There are much more that can be said. But actual answer, and even the C is known. In many cases, C is known. Okay. I mean, in some this thing, there is a very good understanding of what is C asymptotically. So the actual value is not n, it is larger. It's a lower bound, 1 over n, 1 over square root n, remember, is larger. I'll call this C naught. Okay, this is larger definitely, and strictly larger. Okay, so this is important, and I will take a couple of minutes to say some background, some history, without which it will be very boring. But the ideas, whatever I told you, you can do it in any, what is unsaid, you can do it in any dimension D. You can take a function in dimension D, xi's are uniform in 0, 1 to the D, do everything I told you, all the duality, all the supremum, all the computations can be done. You will go everywhere, and what will you get? Expectation optimum n you will get that the lower bound is C by n to the 1 over D. So the more you learn about integration, you learn about multivariate integrals, multivariate calculus, and then you come back whenever you learn it, you come back to these things, you go over this, do everything I said, you can go. There is no obstacle. Okay? Lipschitz function can be defined, integral can be defined, all computations will be done. And at this point, what you will see is you won't get an n, you will get n to the 1 over D in D dimensions. Okay? And now comes what I said is not completely useless, because this bound, lower bound, is correct in D greater than 3. In 3 dimension onwards, this bound is correct. Upper bound is also the same. Nobody knows the constant. Constant is an open problem. The exact constant is an open problem. And in 2 dimension, which is very special, this is C square root log n by n. I'll put it CD, 2, D equal to 2. Okay? So this is what, sorry for the extra time. This was a famous, you can find the list in this thing of the survey of Ledoux. But what I will say is that the 2-dimension result was due to Atstai, Komlosh, and Tushnadi, computer science combinatorics folks in 1980s, D equal to 2, which is where they did. Then there was a lot of contributions in 90s by famously Michel Talleyrand. Okay, if some of you would have heard of him, he was the Abel Prize winner, and one of his contributions for which he got the Abel Prize was the supremum question. Okay, UKH, Shor, Peter Shor, Michel Ledoux in 1990s, coming from probability and statistics. These are statistics plus probability. Then, very important, like I said, I will at least tell you why this is the question that interests me. There were physicists, which includes Giorgio Parisi. For those who know, he won the Nobel Prize in Physics 2 years ago. In 2014, these 4 physicists made a conjecture about this problem in 1 dimension using PDE techniques. Okay, this is statistical physics and PDE. And then this has been solved by Luigi Ambrosio, and then various others, including Felix Otto, who may visit ISI some point in the next year. And these are all using PDE methods. So as you can see, this is combinatorics, computer science, statistics, probability, statistical physics, PDE, including optimal transport. A whole range of people are now working on this question. And there are still many things. As I said, one big thing is to understand in dimension 2 or 3 onwards, what is the precise matching that will achieve this. I think beyond this, the Google Meet itself may be stopped and my students may kick me out. I'll stop here, and sorry for the delay. I'm already kicked out.
Yeah, thanks for the wonderful talk. We'll open up for questions if anyone has questions. Please feel free to.
Let me see now at least. Any questions? Oh, was it too fast or?
So when you started with xi being just uniform, right? So I mean, so it's probably quite. Is it quite universal in the sense that can xi be other?
Let me share my screen. Sorry, this is currently doing this infinite loop. Okay, I can see my screen. Right?
Yeah.
Indeed. in the sense that people do look at these questions on different manifolds, different distributions. Uniform was very natural from the point of view of numerical integration, but you may be integrating f with respect to some other, say, Gaussian density, in which case you may take xi's to be Gaussian random variables. Okay, so and in various other contexts, you may look at xi's being different distributions. What is true? Let's say the constants are a bit of a fuzzy thing. This dimensional picture is very much universal. If it's independent, xi's are all independent. The dimensional, that dimension 3 onwards, it's n to the 1 over d. Okay, dimension 1 and 2, it is n and square root log n by n. Okay, this is quite true. For independent, this is universal. The constant CD, C2, one has to be careful, but this change from 1, 2, and 3, this is universal for independent samples. But if you don't take independent samples, then this becomes a bit tricky. In fact, one of my interests, we showed with some colleague recently, a couple of years ago, in dimension 2, you will not get the log if the samples have a certain specific dependency. Then you will just get 1 over square root n in dimension 2. The log will vanish if, for example, if you take xi's to be eigenvalues of some random matrix or zeros of some random polynomial, this becomes 1 over square root n in dimension 2.
Okay.
Does that answer the question?
Yeah, sure. So, are there any questions? Okay, then let's thank Yogesh once more, and we'll meet again in the next lecture. Thanks once more.
Yeah, thanks a lot. Yeah.